this is the result why it has the thermoelectric, the figure of merit values has become the higher. Because what happened here is that here the long wavelength phonons are very less here, and that has helped the out of three parameters, the thermal conductivity played a major role here. Because of the thermal conductivity higher values in these two type of morphology, we got very lesser values of figure of merit in this case. So the figure of merit which we got it is a 0.67 at room temperature 300 K, whereas so what we have done using this mechanism, so the morphology is the basic thing, so fundamental thing which we can understand, and from there we can try to further do the fine particles. So in order to do this thing, we have just checked, we have gone back to our lab, and we have checked with the two different the surfactant, that is an organic compound surfactant which we have used. When we fixed as a critical point at a 75 millimolar, we got this fine structure. For this structure, we got the highest values of the figure of merit because of the crystals of easily, and where the phonons has get enough place to get scattered. So that resulted in the thermal conductivity. Based on this, we have just checked it out. How we can use it, how this role of surfactant concentration plays in these structures. So here, this is one slide out of the entire the results. When we used it at 50 molarity, you can see for 1 hour reaction, the tellurium powder is left out. So both this structure and the tellurium structure is shown. And for 12 hour reaction, the tellurium powder is unformed, unreacted. And in the 24 hours time it took in this molarity to form a further crystal structure. But still, this morphology is to be seen to check it out how this figure of merit it matters. Whereas this one, it is the one the previous slides I have shown. Now in the 100 molarity when we are used, it has a help. It has a structure where here polars. Here the same thing. Both we got bismuth telluride and BH3 hexagonal forms. Then in this case at polar, earlier here it took 24 hours time to reach this value, but here we reached in polar's time, and also I will show you the further results enhancement here we got it. So this is a morphology for 24 polar and 24 hours here. Here as we mentioned, it is a fine structures. But here at BT 100 polar reaction, we saw the two structures here. I showed you this two crystal structures here. This is started forming, showing the both fine and coarse kind of a structure. Whereas here it has formed the nano sheets rods kind of a structure. So here the thermal conductivity, you can see that it has come down to 0.2 from this 0.1 for this 10-hour reaction, whereas the figure of merit which has enhanced to 0.2, 0.3, 0.75. In earlier case, figure of merit value we have shown 0.67. It is nearly 15% its value is increased for this value. So what is the important thing here is that the thermal conductivity is the least in this material. Bismuth telluride nanostructures is reported. It has come down to 0.29 per meter Kelvin. So this is also what I explained, 0.75. So now overview of the mechanism. Up to now the results I had explained, but what made these materials to get into this parameters? The three parameters here we have used: surfactant concentration and the reaction time. So the bismuth powder plus tellurium powder, this is the EDTA, and we have only taken for one 24-hour reaction time as the concentration we have explained here. When it is below the concentration 50 ml molarity, we got the fine structures, but at 75 we got the structures with enough space in between. For that can place the major thermal conductivity, and then here the nano sheets, rods, and the spherical type of structures we got it. So what could be the reasons of it? From the chemistry point of view, what is the reason? The reason is it's when we use the bismuth powder, bismuth chloride, then the surfactant reaction, and what it happens is that it forms a bismuth. The surfactant covers on the bismuth elements, and when it is below critical concentration, that means below 75. When it is, this is a case I'm talking about when we use the 50 mm, the lower concentration of the surfactant reaction. So in this case, what's happening is that when it is we use the sodium borohydride, this one particles and the tellurium powder are getting separated, are getting mixed in such a way that a thin layer of the formation of this entity it is using, and that's how the reasons the morphology is shown, see, is obtained like this. Whereas when we use the concentration to 75 ml, so that immediately what happens, bismuth and the EDTA, the EDTA is getting covered on the surface of the bismuth elements, and then the tellurium powder is getting mixed. So this could be the reasons of the getting well separated particles here when we use the surfactant at 75. When we further enhance the surfactant concentration, where what's happening is here, as you mentioned here, it is getting formed initially, the surfactant is getting covered on the bismuth ions, and then because of its enough more the volume of the surfactant is a more higher, so that is here we are not using any physical pressure, but that concentration itself is getting like any chemical pressure, and it is helping it to form into the nano sheets. So when it is forming a nano sheets, so these are the reactions. When suppose if this surfactant is not used in this thing, so this could be the reasons. It will come into that one and it forms. It is also forming a bismuth telluride, but the morphology you might not get it. You might not. You will not get it. That could be the reasons. But then in the presence of EDTA, and it is forming into the chemical, you can just later think of it. I cannot explain all these things now. And it is forming a bismuth telluride, bismuth, what I just explained to you, bismuth with the surfactant, and this is helping us, this structures to get a fine particles with the spacious in the morphology. So this is the reactions further. So what is the work is that come out of this using the surfactant, what role it played is, here the reaction time and surfactant concentration 50-75 ml, and the what is the efficiency here. You can see this one, this structure it is when you use the higher concentration, the formation of a Bi2T3. Even from the 1 hour reaction onwards, you got it without having any impurities in between that. So that is the importance, and here how the mechanism is happening in the case of because of this nano sheets, the thermal conductivity it has held, and this nano rods, of course, it got inculcated in this short nano sheets, and that could preferentially help it to scatter the phonons, and that has enhanced the thermal conductivity. So the overall performance when we checked with the earlier work and all, and then we got for this 0.75 is the highest in these materials still reported. And this is the comparison we have done with some of the recent work. In this case, the earlier report also it is a 0.9 highest, it is in 2020 young HF they have reported. However, what achievement using this one we got is that power factor we may got it, but the thermal conductivity which is the least value we have reported here. So here the reduction in 37% in comparison to the presently available state-of-art materials, and the electrical conductivity is enhanced with the twofold. So this resulted in the 15% of enhancement in the field of metal. So this is the summary. This is I had explained to you the same. The surfactant you in the same material, this Ba2 what is available, using this techniques when we use the aqueous method, that means the two elements whose melting point is a very higher, and you should use the liquid, such a liquid, either the water or any other organic solvent whose melting point is a much lesser than this two, and let it allow in further longer reaction time. So that is the result which you got. This is about the things, and I hope I am on time. Yeah, thank you.
Thank you very much.
Thank you.
Now this is open for discussion.
Please.
Okay, thank you very much. Very nice report. You are working with temperature? In which temperature you are working?
No, the reaction we have made it out, that is the boiling point of a water. That is what. After that, what we used, the powders at 373 Kelvin. Yeah, calcined.
In that temperature, actually to control the sigma by K is very difficult. Then how do you control it? Actually, K is K electron and K proton. Then how do you control it?
373 is 100 degrees centigrade only.
Even then, which of the part is better? I think proton part is excited.
So see, exactly the deep insight into the material we did not. So what we explained is that based upon the chemistry, I just here it is that what it has happened, this presence, it is helping this bismuth elements get separated. It is not allowing it to mix with the temperature at that time in the presence of that one. So slowly when it is covered with the EDTA whose melting point is higher than this one, it is getting protected and then it is getting added to the tellurium one. And at 100 degrees centigrade, so this could be the reasons we have not used any other parameters, but you see the different kind of a morphology, whereas it is a fine structure, but it is a separator, when it is a nano sheets and all. So what could be the reason of it? When the phonon gets scattered in the longer path, you can see that one, where here there is no space. That is the similarly to the bulk. In bulk, why the thermal conductivity you cannot decrease because of the grain boundaries, which is the error limit is fixed. So this is the understanding, this is the interpretation we gave in that one. So for further things, you can just see refer this to for a clear work.
If there is no question, thank you very much, madam.
Thank you, sir.
Nice presentation.
I request our session chair, please present the momentum to our honorable speaker.
Now, next speaker is Aparna Chakravarti. She is from our architect. So time depends on you.
Because she has told many of the things which I wanted to know. Really, I speak very loudly. Okay, so first of all, I would like to thank the organizers and of course all of you to be present to listen to my talk, and specifically I want to thank all the student volunteers because they are working round the clock and very hard. So thank you very much, all of you. Yes, they should get a party from the organizer.
From the speaker.
No. I have to borrow the money, that's all. Okay, so as chairman said, I am Aparna from Rajaramana Center for Advanced Technology, Indore, and this is our Indus building, and this is the Homi Bhabha building at Arakat. I have affiliation with both, and this just to show you that this is our Indus 2 experimental hall. And as everybody is telling, I also want to say that you can go to Arakat website, all the students, and you can ask for beam type. And we have two synchrons, Indus 1 and Indus 2. So these are my group members, and when what I will talk is on this is work of Rajiv Gar. So motivation is that Heusler compounds and thermoelectrics. So, and there are many other possible applications of Heusler compounds, but I will be speaking on that. So already Vasundhara has talked about thermoelectricity, so I need not take just one more. We are just brushing up. The thermoelectric parameters are Seebeck coefficient, the thermopower S, power factor S square into sigma, electrical conductivity, and figure of merit. This is S square sigma into T by kappa. Kappa is actually the thermal conductivity. We just do contributions, one from electrons, one from photons. So, Heusler alloys, just in brief, that most of the Heusler alloys, these Heusler alloys are of two types, full Heusler alloy and half Heusler alloy. So full hydroxide alloys are of the formula X2YZ or XYXZ, and these are called having conventional structure. This is inverse structure, and then typically XY stand for transition metal, and Z elements are the SP elements. Typically, many of them, specifically the full hydroxide alloys, undergo cubic to tetragonal transition. And this is just the schematic, and most well studied hydroxide alloy is the Ni2MaG, which has been discovered in 1984. It is a ferromagnetic shape memory alloy. And many of these are I am talking about the full hydroxide alloys. Many of the half hydroxide alloys, they don't undergo this kind of transition. So why hydroxide alloys for thermoelectricity? There are various systems which are considered good thermoelectric materials. So tellurides, just Vasundhara said, touched upon. She has talked in great detail. Selenites, clathrates, zinc. I can explain to you in detail if you come to me. I am not going to explain much of these structures. And for example, half hydroxide alloy, which is FeTASB, which has a high power factor and high figure of merit about 1.5 at 1000 K. Because here also she helped me. She said that these are mostly mid to high temperature alloys, which are useful alloys for high temperature, mid to high temperature range. So hydroxide alloys, specifically half hydroxide alloys, which are of formula as I said XYZ. Out of this X2YZ structure, one of the sublattice is empty. So they exhibit good thermoelectric and spin injector properties, and many of them show semiconducting nature with suitable band gap and carrier concentration. Thermal stability is very good for medium to high temperature operation. The elements which are present, they are abundant, available, and low cost, and sample making is very easy. So, because just previous to me, Vasundhara's talk was there, the job for me became very easy. So, I am using density function theory. So, this is a purely theoretical talk compared to us. So, we do optimization mostly using VASP, and after that, structure optimization. We do electronic structure calculation using Win2K software, and then transport properties we have done using Bootstrap. So our work is like, we are mostly concentrating here in this talk on CO-based alloys, CO-based full and half hydroxide alloys. So Kubler et al. Showed that many of them are half metallic. That means one channel is metallic, one channel is semiconducting. All of you know that. And study of hydroxide alloys, some of them have been done. Then they are shown to be good thermoelectric materials. And then recently, cubic phases of CO2-TaSi and CO2-TaGe exhibited good thermoelectric and spin injector properties. These are the papers of other people. So here in this talk, in this work, what we did, we studied the electronic and thermoelectric properties of COX, TaZ, X equal to 1 and 2, and Z is equal to Si, Ge, and Sn. Our job, aim, threefold. One is to explore if any of these show any kind of tetragonal to cubic to tetragonal transition, and then compare the thermoelectric properties of all these 6 materials in cubic as well as possible tetragonal martensite phase. And third is, which is the most important, to understand thermoelectric properties in detail in terms of electronic properties. This is the most important point here. So just for completeness sake, I will explain the first 2 points. So first is tetragonal martensite phase. So what we do cubic structure, and then we vary the C by A, keeping the volume constant, because the martensite transition is known as volume constant transition. So we keep the volume constant as the cubic. So for this we optimize the value of A, then we vary the C by A, keeping that volume constant. Then we plot energy difference between M and A, M phase and A phase, and we calculate our tentative Tm value, that is the transition temperature value. This is a crude approximation just to get a trend. So we see that formation energies of all of them are found to be negative, and when we vary the C by A, we see only the full hydroxide alloys, they show a typical tendency of lowering of energy at a C by A value higher than 1, but on the other hand, all these 3 half hydroxide alloys, for them, this is the cubic phase is the lowest energy, found to be lowest energy, and this is expected. So this is just to say about structure and magnetic properties. So what we find most important thing is that we have compared with literature wherever the values are available, and few of them are available already. C by A values we have calculated, because martensite phase nobody has done, nobody has touched. So these values we have predicted, and we find that all the half Heisler alloys are non-magnetic, whereas all the full Heisler alloys are magnetic in nature. And formation energies are there, and there is a train, and also in lattice constant you can find some trains which are listed here, details of which we can discuss in later separately. So delta E value, which is the energy value which I showed. So these are the values, the difference between martensite and austenite, and these are the TA values. So what we see is that CO2 TA shows the lowest energy of transition compared to the other two, and this is that means it will show a martensite transition below the room temperature. So elastic properties are always calculated because, as Professor Pandey also said, these are very important properties, and many of the things one can discover or come to conclusion on the basis of elastic properties. Here I am just touching on the stability criteria. So for cubic symmetry, these are all the elastic constants, as well as C prime tetragonal shear constant, and G is the tetragonal constant. This is G is the shear modulus, B is the bulk modulus, and G by V value is the measure of the malleability. So when it is close to the value of, there is a empirical formula given that when this G by V value is greater than 0.57, these materials are not so malleable. So which shows that these are the half Heisler alloys are kind of in that range, but on the other hand, the full Heisler alloys are supposed to be malleable, so they are good. And tetragonal phase also we have done all the calculations, and we see that both cubic symmetry and tetragonal symmetry, they, whenever it is applicable, all these phases are stable from the elastic properties also. And just to cover this density of states, to show that these half Heisler alloys are all semiconducting in nature. Here are the listed values of band gaps. On the other hand, when we see the full Heisler alloys, all of them at the Fermi or very close to Fermi, they show a very high density of state, which is this black lines, and which already indicates that these are not so stable at the cubic phase, at least in the zero temperature. In higher temperature, the situation can be different. So, higher temperature, there is a splitting, which is a Young-Taylor distortion, and this is very famous for these full Heisler alloys. And this is the reason for this Young-Taylor distortion, because of the symmetry rating. They are more stable in the lower temperature in the martensite phase. So then second is to compare the thermoelectric properties or transport properties. So these are the electrical and thermal electronic conductivity values, sigma and kappa. Kappa this is only the electronic part, because in this particular one we have done only the electronic contribution. We did not calculate any of the phonon contributions. In our later one we have done, but not in this one, because in this one we are just interested in getting some kind of trend. So here the seabed coefficient, in seabed values also there are certain trends which I will come in little later in detail, because I will be touching on the electronic structure. So here also some figure of primary values. We have some trends. So we see that order of magnitude of S values, HHA is higher, FHA in A phase, and then FHA in M phase. This is the lowest. And similarly for this is the order of magnitude of the ZT value. HHA greater than FHA and then greater than FHA. So we wanted to know what is going on. So for that we have to understand the electronic property. So to understand the thermoelectric property, we have to go through the electronic property, specifically the band structure and the Fermi surface topology in detail. So what we find, this is where I have plotted the band structure for the cubic phase this CO2 TASI, CO2 TAGE and CO2 TSN, and these are the downspin, this is the upspin, because these are the magnetic materials. So we see that upspin channel, there are some upward shifts and there are some details, but I want to mention that we see some linear dispersion like features very near EF in certain directions in both the spin channel, and both flat band, because here I have talked about flat kind of bands also. So both flat band and linear kind of dispersion have important implications, which I am not talking about here, but I just wanted to mention. And this is the band structure of the tetragonal phase of the full Hustler alloys. And here we see the flat bands are missing, but finally what we see that linear like dispersions are still there, so this is also important. Now, in detail, I first go through the half Hustler alloys. So half Hustler alloy, these are the band structures and these are the Fermi surface again. Sorry, as written that B and C, B is like these are semiconducting materials. So there is no Fermi surface as such because there is no crossing. But what we do is because in temperature, when we have higher temperature, then transitions can happen slightly below Fermi to conduction band, like in case of semiconductor, that is what happens. So what we find is that what we do is we take a valence band maxima, we identify the valence band maxima, and then we take certain amount of we check where it is positioned. So this, for example, in this material COTA side, this is almost touching, this is slightly below, and on the other hand, this is the valence band. We have it is in the inset. It is shown in a zoomed situation, and these are the conduction band. These are slightly higher, and these two valence band maxima. In all the cases, they are very close to Fermi level, and they are very. The difference between these two are listed here. For example, for these two, the energy difference is delta V. The energy difference between V1 and V2, this is 19.93 MeV, this is 52, and this is 64, very close. So at these values, 25 MeV below the VBA, so which we consider these peaks, and 60 MeV above the CBM, because we see that CBMs are kind of higher. So we take above 60 MeV above the CBM and we calculate the Fermi surface. So this conduction minimum has been observed at a certain point, and valence band minimum has been observed, has been observed for certain points. For example, in case of W, point W for SI and point L point for GE and SF. So we see these are the Fermi surface contours. So now I want to point to the fact that valley degeneracy and Fermi surface area are very important in terms of governing the thermoelectric properties. So for good thermoelectric materials, as Vasundhara has already mentioned, there's high thermo power, high power factor, high figure of metal needed. What we find that for COTA SI, if you remember, I don't know, maybe you just take my word, that these were highest. For COTA SI, the values were highest. ZT values and thermo power values also. So this is because of the higher NV values. Now what is valley degeneracy? So it has been seen in the literature that coefficients, that is S values, are proportional to the total valley degeneracy NV, which depends on number of valleys and degeneracy of states close to EF, as well as symmetry of the Brillouin zone. The higher the symmetry of the point, high symmetry point, along the band directions we have done around gamma, W, L and all. So the higher the symmetry of the point, so higher the number of symmetry equivalent position also. So this plays a role, and S also depends on the shape of density of states at or close to EF. Then there is a direct relationship between electrical conductivity and Fermi surface area. That also we all know from our MSc or BSc level. So number of states available for conduction increases with available surface area. And then kappa, as I said, has two contributions, electronic and lattice. As per Weidemann-Franz law, we calculated only the electronic part, which is proportional to the product of temperature and sigma. So higher sigma, often higher kappa also. In that case, the phonon contribution of kappa comes to help. But what in this we did not, as I said, we did not do the calculations, but we just compared the electronic part of it. So basically the higher NV value indicates for COTA SI, why we get the better thermoelectric properties. So band structure and topology of the full Hustler CO2TA SI. So here also austenite phase and martensite phase we have plotted band structure just to show the band numbering corresponding Fermi surface, and this is for up and this is for down, and this is for martensite phase also up and down. So we see that A phase has higher crystal symmetry, So these are the Brillouin zones, and these are the high symmetry points around which we have plotted the band structure shown. So A phase has higher crystal symmetry and higher number of values also in A phase. So we get higher S values for A phase compared to M phase, because that was a confusion for us why the A phase is having higher values compared to M phase thermoelectric properties. Similarly, for CO2 TAGE also, similarly we have observed the same thing. Here I just show because the band structures are very similar, so I show only the Fermi surface and the areas, Fermi surface areas. And again, the similar for CO2 to ASN also, it is very similar. Band structure is similar, and so due to lower crystal symmetry and less NV value, so M phase has lower S values as in cases of Si and G. And we have seen the for M phase S values are varying in a little bit different ways. There is not much systematic, but since these S values are too much low, and so critical matching could not be meaningful. So I come to the conclusion. So probed martensite phase, these materials x equal to 1, all these show stable tetragonal phase, all the full raster formation energy, density of state and elastic properties confirm the stability of cubic and tetragonal, and it indicates the density of states indicate why austenite phase will be less stable compared to the martensite phase at lower temperature. And then compare the thermoelectric properties. So just to reiterate that S values, HHA is greater than FHA in A phase, greater than FHA in M phase, and similarly ZT values also, it follows the same. So from the band structure and detailed analysis of the Fermi surface topology, we could explain the complete comparative behavior of thermoelectric properties. Tetragonal phase for FHAs has lower values due to less NV and lower crystal symmetry. So cubic symmetry will be best choice according to us, and then much higher S values of HHAs yield higher Z values. And take home message number 1, there are 3 ways of doing research. This is for only the students. So one is theory, this is Einstein, and this is simulation which we are doing, and this is experiment. This can mix also, but typically these are kind of, most of the time they are separate. So you can see the experiment, they are having trouble, and then this person also is having trouble. On the other hand, the simulation person is jubilant. And take home message 2, that ZT value improve thermal, you know this S high, sigma high, kappa low we need, and improve the higher S value, higher sigma and lower kappa value. And materials should be for experimentally viable. They should be energetically stable, mechanically stable, thermally stable, and also dynamically stable. So I did not show these 2. And so the take-home message will be do computer experiments first. And I am here talking about the bulk because what Vasundhara said mostly nanostructure, but I am mostly talking about bulk structures here, bulk materials here. So you can calculate or predict band structure, Fermi surface topology, and if needed to reduce kappa, you introduce dopants, defects, and disorders to take care of the phonon part of it. Electronic part, as I said, it depends on the sigma, so you cannot control it much, but you can control the phonon part. To reduce kappa, you can work on that, work on the samples. So with inputs from that, you make your sample and do actual experiments. So that will be the take-home message from this talk. And acknowledgement, as I said, I thank all the organizers, specifically the student organizers, and of course Anurag, for giving me a chance here. All members of our section, director, group director, members of some group boards and all, Computer Center, HBNI Mumbai. And finally, thank you all. This is a picture from our Sukhnivas Lake. So thank you very much.
Thank you very much.
How much time did I take?
Now presentation is open for some questions. Yes.
Yeah, no, thank you very much. Very nice talk. Actually, that boot trap only, it does not contribute the phonon part.
No.
Boot trap code. So is there any other code to calculate the phonon part?
We are doing, there is some formula, this Slack, it's main author is Slack. So we have other papers where we have done this calculation also, and final ZT values we have calculated. Here our main aim was like to understand, like first of all, to whether these elements, these materials show tetragonal transition or not. And then second, when we did the calculations, we see that there is like orders of magnitude difference in the ZT values. So why is so? So from the details of electronic structure, we try to understand why.
Ma'am, one. So this Win2K software you use, right? So these calculations, the phonon value or this, can you predict very accurately use with the nanostructures?
Nanostructure using our resource, we cannot do. You can predict because Win2K is a all electron source, a code, so it's very accurate. But nanostructures, if you want to do, because that you lose the periodicity, so we cannot.
Is there any better simulations for this nanomaterials prediction?
Nanomaterials for these kind of like if you are going to predict in a very accurate way, I would say you have to do
But
this kind of ab initio.
Yeah, based upon the science, I understand that why it is not possible in the nanostructures. But I have seen some of the publications where they use a very
Model calculations people are doing, but there like you do not probably get that much accurate values. And if you are you are interested in just a trend of values, so you can always use some model calculations and then try to do. And there are several modes. I am not very yes.
So first is comment.
Good.
It shows slide number 23.
23. There is a mistake. I am sure. Otherwise, you would not have known.
23.
I go. Now I go. नहीं जा रहा.
Yeah. Oh, the mistake is
No.
no,
This is
no,
very
no,
clear. That is
that
no,
ego
no.
message only.
The mistake is simulation people are not very happy all the time.
We
We also
are.
have our own struggle.
We are because we don't break any beaker. We don't break any machine.
Ask a student.
You ask her how much trouble she has to undergo.
That's fine. But,
Compared to that, we are sitting in the computer.
but second question is, like you said, you related nicely NV to the ZT factor. So for a given, say, half infraroids, it goes from silicon to germanium to tin. NV goes down. So do you have any insight? Means why is so? Is it just because of the delocalized electronic density, or you have a
The NV value.
NV value?
So the degeneracy, as I said, if you take silicon germanium tin, you say, if you are talking about cubic symmetry, then the valley degeneracy will be the same. Okay, so then it will depend on like how close it is to the Fermi surface. So that also will matter because you see in ZT you need S value, sigma value, and then kappa value. Of course, if you are talking about pure crystalline tin and silicon and all, you don't bother about that. But S and sigma, these will be very much related with how close to the Fermi level the states are, and then how much degeneracy.
Agreed. So in the periodic table, as you go down, then you expect a more degeneracy or less. What is the expectation? Because you're following the trend.
See, I don't know. I have to think about
We'll
it.
talk. Thank you.
Yes.
So you consider F electrons or
Like TA?
yes?
TA? If it is there, because for Wien it is all electron calculation.
Yeah,
So it will.
then I mean yes, of course, all electron calculation, but how do you place the F electron levels, like from experimental guidance?
No. We do the band structure calculation like from ab initio level. So we give our basic structure is the structure, basic input is the structure as well as the whatever in Wien, whatever exchange correlation you are using and things like that. So you like if you are talking about mass then you talk about which pseudopotential you are taking and how you are whether you are incorporating F in this or which ones you are incorporating the balance and all sorts of things are coming.
The Fermi surface has F electron contribution.
Fermi surface, as far as I remember, I don't think F was there. I don't remember because they TA. I forgot now the electronic configuration. So F electrons, maybe I don't remember now. Like how close it was for the Fermi, but it was mostly, as far as I remember, it was mostly dominated by CO D states. As far as I remember, which when we did the partial density of states, as far as I remember, but I cannot be 100% sure at this moment.
No,
I could ask her later, now or later.
Later is better because we are running short.
We have 2 more lectures.
So since we are hard pressed with time, or maybe.
We have 2 more oral
Yes, yes.
presentations. Thank you very much, madam. Now we have a,
Then you should have it twice because I think well in time. No?
but 10 minutes in discussion.
That I cannot take time. Thank you very much.
Now we have 2 presentations from short period, that's for 10 minutes. First one is MS Sarkar.
Yes, but the title of the talk is
Title is not MS Sarkar from West Bengal.
yes. Actually, I have 2 parallel session talk. So my actually the clear concern about one. I have one PhD laboratory, system design laboratory, and I have 2 parallel session talk. So that is why actually my student is giving the PhD student. She is submitting the thesis. So she will be giving this talk, and there will be another talk. So the forecasting part, actually we have 2 parts. One is seasonal forecasting, so my students will be delivering that.
Next one. Now next is Dr. S. Misra from Kanpur. So now you can.
Good evening, everyone. My name is Pallavi Bharti. I am from Macaut, West Bengal. I am here to present on the topic macro trend-based seasonal solar irradiation forecasting for potential energy applications. Basically, we are doing for the solar PV, but all the results are applicable for different energy applications as we are using the forecasting methods over here. The major importance of our work is related to the operation and maintenance of PV systems, where we see that there are various algorithms which are predicting on for short-term forecasting. But we are trying to take out the seasonal forecast, which is the need because we have seen that there are situations where we need the seasonal forecast to give a good accuracy of good planning, and the second thing is reschedule the different types of system which needs the rescheduling, as the complete renewable systems are not included in the completely the system. The electricity supply has not become dependent on renewables. The second important point that we are considering over here is the hydrogen and the battery storage systems. So what happens is the compatibility with the PV is there is a huge compatibility of hydrogen systems, hydrogen storage systems with the photovoltaic systems because of the low DC voltage. Then they can also be transported through the pipelines, and for the battery systems we have the scheduling of charging systems, and contingency mechanism has to be set up for the battery the scheduling of charging and charging process of the battery, as we need to store the energy whatever we get from the PV. Also, we need a forecasting seasonal forecast for the agriculture purpose, where different crops need different types of seasonal cycles. So those portion also the seasonal forecast is very applicable. And the next importance of our work is related to the where we can maximize the irradiation inside the structure, which will reduce our dependence upon heating and cooling systems. So this is just a small view of how the irradiation falls on the earth. The major part here I would like to say is the focus of our work is GHI, which is the cross horizontal irradiation that is falling on the photovoltaic panels. And this cross horizontal radiation is becoming undeterministic after crossing the atmosphere. because it is affected by clouds and other portion. Now here the issues and challenges which we get in photovoltaic systems are that irradiation is stochastic in nature, and the availability of irradiation data values which can be captured through high cost pyranometers or pyroheliometers are not available everywhere. So the data is very less. And there, as I mentioned in the past also, that sophisticated forecasting algorithm is present for shorter time scales like 24 hours, day ahead, or even more shorter scales. But seasonal forecast is not there. And also one more important thing here is that very few studies for the eastern region of India. There are forecasting for the western and the southern region of India, but the eastern region of India lacks such type of studies. And we in the irradiation profile, we are exploring the irradiation profile of West Bengal, which is lying in this in a dynamic region, which is a dynamic region. The background studies, there are some works on seasonal forecast from which we have been motivated. So here we have the Beth et al. Who have forecasted the energy for both the wind and the solar power, and they have predicted a high dependence of the power forecasting on irradiation. Then we have the seasonal model. There is a seasonal model that has been proposed by WAN. They are proposing a seasonal adjustment factor. There are some more studies which are also laying importance on the seasonal forecasting. The basic thing that we are going to which is our objective over here, is that we are accurately forecasting. We are trying to accurately forecast seasonal solar irradiation for a particular site and for a univariate variable. So here, what is the novel thing that we are trying to add over here is that only based on with the help of GHI, we are trying to make an accurate forecast for a particular site. The methodology that we have followed is data acquisition, and then we have tried to make a forecast model on the basis of macro trend. Then we found some problem in that methodology as there was a appreciable deviation in the forecasted value. So we tried to do a exploratory complete data analysis of the irradiation profile of West Bengal. Further, we are focusing on formation of grouping of seasons and then forecasting. So the data has been acquired from the NASA Power website, which has the following resolution of 1 degree latitude and longitude wise. And this irradiation forecasting has been done for Krishnagar, which passes through the Tropic of Cancer, and it is a agricultural bed. And also this location has been chosen by IMD Pune for there has been a automatic weather station has been set up over there. Here, what we started previously with our work was as it follows in economics, that is seasonal indexing. We were inspired to those methods to use the seasonal indexing and then moving average. So seasonal, we used a multiplicative model where we multiplied the seasonal indexing with a moving average to predict the seasonal forecast. But here we saw that there is some pattern in the seasonal index. There is a increase, then a decrease, and further a decrease, and we found two maximum points which can be seen in the seasonal index graph. But after that, when we forecast it, there is a deviation in the not deviation. There is some appreciable differences in the values which we are getting. That is almost 21% with the NASA values and 19% with the plant that is actually installed in our campus. So there we investigated it further and found that we cannot use seasonal indexes as it is used in economics, because there is a where they use the monthly variation, but here we see that there can be 2 or 3 months which can be grouped together to form a season. So we have gone through this approach, which is the very basic run exploratory data analysis from the run sequence, box plot, histogram, and autocorrelation. Here we found from the run sequence plot of almost 10 years that for 10 years, so it was almost 120 graphs which we analyzed for every part of the analysis. From here we concluded that there was no stationarity in our graph. To see the general trend, we did this, and we concluded that there is no stationarity. Then from the we have grouped a mean, and then we for each year, and then we saw that there are some patterns which needs to be further examined. From the box plot, we have taken out all the basic summary statistics, that is the central tendency, PKS, and the spreadness of the graph, where we found that the month of July is highly variable. From the histogram, we can see that there is a skewedness in the data. And the autocorrelation plot, which is telling us about the periodicity in the graph, and that again it is pointing it out that the data is not stationary. There was a pattern which has to be decomposed. So the actual data, the trend, the seasonality, and the noise has been bifurcated. And on the basis of this, we have tried to take out a magnitude, a quantitative value from here, that is the trend index and the seasonal index. Finally, our future work, which is depending upon, we have decided that we are going to do the grouping of the solar season, which has already been done to some extent on the basis of the IQR. But here we are trying to do it on the basis of PCA and K-means clustering, and then we will be forecasting it. So basically, the work will be to predict, to group our seasons, to make a new season, which is the solar season, and on the basis of that solar season, we will be trying to do the seasonal forecast. So for the PCA, it is a univariate, we are using a univariate time series data over here, that is only the GHI we are using. But the thing is that PCA is mostly used for several variables. So what we have tried to do here is that using the statistical features of the data. So by using these as the variables, we are going to...
You have only 1 minute completely.
Okay.
10 minutes.
So we are just going to use these variables in the PCA to group it, and then finally we will be using this algorithm as for grouping, and then forecasting by using moving average or some other methods in future. We highly acknowledge DST West Bengal and MEGAUT West Bengal for the infrastructural support, and also I would like to acknowledge NASA Power project team for the data source, for providing the open source data. These are my references. Thank you.
Thank you very much. We have a chance of one question, please. If there is no question, then thank you very much. Now next one is S. Misra. You have 10 minutes only for presentation.
A very good afternoon to all of you. My research topic is, presentation topic is novel nano-based advanced technologies for the removal of hazardous radionuclides and heavy metal ions from groundwater. In this presentation, I will discuss 4 publications of mine. First, which is published in RSC Advances, second one is in MJC, and third one is in RSC Advances. And After explanation, I will go in second part, Journal of Membrane Science, which is published in 2020. As we all know, water contamination is a global issue. There are so many sources by which water is getting contaminated day by day, like domestic wastes, industrial wastes, agricultural wastes, or nuclear wastes. Dumping of huge radionuclide wastes and industrial wastes containing heavy metals in water stream raised global concern due to their global existence and severe toxicity. Due to its severe toxicity, high accumulation and non-biodegradable tendency, it is severe environmental concern to remediate these hazardous contaminants like radionuclides and heavy metals from water. This slide representing the assessment data of uranium, chromium, cadmium, and various heavy metals and radionuclide ions. In literature, there are so many removal technologies are available like ion exchange, precipitation, coagulation, microbial biodegradation. But these found severe issues like high investment and running costs. Some technologies produces toxic sleds. Some technologies have high-tech operation and maintenance costs. So, to view of the severe deterioration scenario of the water quality of various states of India, it is highly desirable for us to develop novel material-based technology to remove radionuclides and heavy metal ions from water. In literature, so many technologies, but I have chosen absorption technologies because of ease of operation, its simplicity, economically viability, and no involvement of any pre or post treatment. In commercially, there are so many available adsorbents also available in literature, and various studies are performed by use of activated alumina, ion exchange resin, clay, tops, and many more. But these adsorbents are having some problems like activated alumina produces toxic sled, ion exchange resin, high-tech operation is required. In the case of clay, high reaction time is required. In the case of top, chemically unstable. So I developed 5 types of advanced nanomaterials. First one is tributyl phosphate functionalized carbon nanotube. Second one is zero valent iron decorated carbon nanotube. Third one is thiofunctionalized carbon nanotube. Fourth one is iodide functionalized carbon nanotube, and the last one is cellophane functionalized activated carbon fibers. So basically, the matrix of all these materials are carbon nanotube and activated carbon fiber. Here the question arises: why I chosen carbon nanotubes? Because of its high radiation and thermal resistance, operates at wide range of pH. It is chemically stable and large surface area. And why I am choosing activated carbon fiber? Activated carbon fiber I purchased from Japan, and this is having large surface area, thermostable, and low acid and base reactivity. This slide presenting how I developed carbon nanotube in laboratory by using chemical vapor deposition technology. The main advantage of this method are as follows: there is no need to use explosive hydrogen during pyrolysis. I use nitrogen for the making of carbon nanotube. Cost-effective technology with large-scale production and the use of less toxic ferrocene as a floating catalyst, and the synthesis of carbon nanotubes I prepared without any substrate. After the development of carbon nanotube and pre-treatment of activated carbon fiber, various functionalization was done by various functionalizing agent to develop tributyl phosphate functionalized carbon nanotube, to develop zero valent iron decorated carbon nanotube. Third one is thiofunctionalized carbon nanotube, and the last one is iodide functionalized carbon nanotube. And this is the representation how I prepared cellophane functionalized activated carbon fiber. After the functionalization, these developed materials are applied for the removal of uranium and antimony and found the removal efficiency very good. This representing the FTIR data of developed nanocomposites before and after removal of radionuclides. This is the experience data of ACH cellophane and CNT-TBP before and after removal of uranium. Here we can see uranium peak is observed. Here uranium peak is observed before and after removal of uranium. This is plain uranium activated carbon fiber. This is oxidized activated carbon fiber, doped uranium, and this is cellophane oxidized activated carbon fiber, doped uranium, which get high peaks of uranium. This is the experience data of zero valent decorated carbon nanotube, iodide functionalized carbon nanotube, thiode functionalized carbon nanotube before and after removal of antimony. It is evident from the XPS and FTIR data that chemical absorption takes place between contaminants and developed materials, which is responsible for the removal of contaminants from their corresponding developed materials. This is the recyclability studies. Now I am going to the second part of this presentation. Although the removal efficiency all these developed materials is very good, but these developed materials are used for the removal of single contaminant at a time, not simultaneously. So I proposed a plan to Department of Science and Technology to develop a novel material which can remediate a water from heavy metals from water simultaneously. For this case, I prepared two types of another nanoparticles, ferrous sulfide nanoparticles and carboxylic oxide ferroferric oxide nanoparticles by solvothermal method. After the synthesis of these advanced nanoparticles, these nanoparticles were doped inside the PVDF matrix. PVDF matrix I used and embedded these two types of nanoparticles in it. First, I prepared unmodified PVDF membrane having no any nanoparticles. Second one is in PVDF membrane having FES nanoparticle. Third one is PVDF membrane having second nanoparticle, which is carboxylic functionalized ferroferric oxide. And the last one is PVDF in which both nanoparticles are added. Characterization and membrane properties and separation efficiency of all these four membranes were evaluated and found that FES, CFFO, PVDF, both nanoparticles of membrane is highly efficient to remove multiple metal ions simultaneously from the water. This is the protocol of FES, CFFO, PVDF mixed matrix membrane. FES nanoparticle and CFFO nanoparticles are doped inside the PVDF and DMAC and PVP polyvinyl fiber dope, and by using phase inversion process casting is done and dipping in a coagulation bar to prepare a membrane. This is the characterization of all these membranes, and in this characterization we can see no any visible agglomerates of nanoparticles inside the pore structure, indicating that nanoparticles were very well dispersed in the PVDF matrix prior to the casting. This is the AFM images of all these fabricated membranes. This is the simple PVDF having no any nanoparticles. We can see here roughness is around 67.2 because there is no doping of any nanoparticles. And in the case of B, we can see here roughness decreases after doping of single nanoparticle, which is FES. In the case of C, which is CFO PVDF, in which roughness is again decreases from 48 to 30, and in the case of both nanoparticles embedded membrane, we can see here the roughness is 28.7, which is lower than all these three membranes. So we can see here decrease in roughness attributed due to the hydrophilic nanoparticles on the membrane surfaces. In general, higher surface roughness having tendency to getting fold. So in this case, both nanoparticles are added, so hydrophilicity is increases due to the high hydrophilicity. Folding effect will be lesser. So we can evaluate that all fabricated membranes have also ability to prevent from the addition of unwanted particles on the surface due to the continuous decrement of roughness. This is the FTIR spectra and water uptake capacity of unmodified PVDF and nanoparticles embedded membranes. With increase in hydrophilic site present on the membrane surface, affinity of the membrane towards water increases, thus more will be the water uptake on the membrane surface and less will be the contact angle. Here we can, next slide we can see this contact angle study. By loading of nanoparticles, voids and cavities are formed between nanoparticles and the PVDF matrix due to heterogeneity, which increases the amount of water content, leads to the higher water uptake capacity. This is the reason behind it. This study show the water contact angle. This is the mechanical and chemical study, chemical stability study. And this is the permeation performance of the fabricated membrane. Here we can see FES CFO4 nanoparticle doped PVDF membrane having low contact angle. Due to low contact angle, flux will be high. So we can see here the unmodified PVDF having high hydrophobicity. Due to the high hydrophobicity, water uptake capacity of permeation performance for water flux is very low. Or in the case of FES CFO4 PVDF, in which both nanoparticles are added, flux is very high in comparison to all these three membranes. So we can conclude this: the enhanced permeability of the fabricated membranes is consistent with the water uptake, contact angle, porosity, and membrane morphology parameters. Loading of different types of hydrophilic nanoparticles like carboxylic puncturized hydrophilic oxide nanoparticles enhances the hydrophilicity of the PVDF membrane due to the elevation of hydrogen bond interaction between water molecule and surface of the membrane. By incorporation of hydrophilic nanoparticles, the dense polymeric chain packaging is obstructed, introducing more free volume for water molecules passing through. This is the separation performance of fabricated membranes. FES PVDF membrane was examined only for the rejection of chromium. Second one is examined for the rejection of cadmium and lead, and the last one is for the simultaneous rejection of cadmium, lead, and chromium. These are the reaction mechanisms. And this serves one. The applicability of this membrane is applied in neutral as well as in acidic pH. In acidic pH, in neutral pH, FeOH and COOH present in its ionized form, responsible for the negative charge on the membrane. In acidic form, protonated form will be generated. So due to this, positive and negative charge generated on the membrane, positive and negative charge species will be, some species will be absorbed and some species will be rejected. That's why the absorption that's why the overall separation takes place. And then this membrane is applicable for the treatment of groundwater contaminated with hazardous heavy metals. For this, I used the industrial area, water of industrial area of Kanpur, Jajmau and Rania, and study concluded a single step filtration of this contaminated water through developed membrane. It was observed that developed membrane is highly efficient to bringing down the concentration of multiple heavy metals into WHO limit. This is the evidence of the interaction between fabricated membranes and the metal ions using XPS. We can see here curve-fitted high-resolution scans of FES CFO4 PVDF membrane after filtration of metal ions for chromium, cadmium, and lead. We can see here after filtration we study the XPS, which evidence that chromium is separated out, cadmium is separated out, and lead is separated out. So we can see here interaction of chromium, lead, and cadmium onto FES CFO PVDF is validated and evident from the appearance of double peak of chromium 2p 3/2 and chromium 2p 1/2 and double peak of cadmium 3d 5/2 and cadmium 3d 3/2 and lead and so on. Additionally, splitting of multiple peaks are observed for the 2p 3/2. This is 2 peaks are separated, which suggests that the reduction of chromium 6 to chromium 3 from FeS nanoparticles, Fe2 plus and S2 plus play a key role in the reduction of hexavalent chromium. And finally, I acknowledge Professor Jayan Kumar Singh of Department of Chemical Engineering, IIT Kanpur, Professor Jaya Dwivedi ma'am, Vanastari University, Dr. Nalini Shankar ma'am, IIT Kanpur, and I highly acknowledge Department of Science and Technology for DST Young Scientist Award, and warm thanks to all group members for their cooperation and kind support. Thank you so much.
Let me come up one question. Madam,
Yes.
Yeah.
Actually, very good to the presentation. Actually, just a small question. So, did you compare your membrane with the commercial membrane?
No, sir. Actually, there is a problem behind it. I published the paper in Journal of Membrane Science, but here the problem in this study actually chromium, lead, and another one is what? cadmium, lead, and chromium. Three species are rejected from. But
do you try for diet mobile or
हाँ
any other
ये मेरा फ्यूचर वर्क है सर कि मैं फ्यूचर में इन सबको
organic
हाँ वो मैं देखूँ उसमें वही मेरा फ्यूचर प्लान है इसके और क्रॉस प्रोफिटेशन के बाद के द्वारा मैंने इसको परफॉर्म किया हाँ यस सर मैंने दिखाया उसको
Thank you very much. Now this session is over. Now we will again meet after tea break. Sir, tea break. Okay.
Let us have a quick tea break for 5 minutes, just 5 minutes, please. Please come back in 5 minutes so that we can have more fantastic speakers.
Food.